Now we're going to begin discussing studies that collect individual level information, starting with cross-sectional studies. In a cross-sectional study, the relationship between a health outcome and some variable of interest is assessed as they exist in a defined population at a given point in time. In its simplest form, a cross-sectional study is going to measure the presence or absence of a disease and the presence or absence of an exposure at the same time. The analysis of cross-sectional data often looks like a case control study, though what we're calculating is the point prevalence rate for the outcome of interest, and that's what we're going to estimate. A cross-sectional study can be useful to assess the prevalence of disease, but the major drawback to this design is the inability to examine the temporal sequence between exposure and disease because we're assessing both of these simultaneously. This figure depicts a cross-sectional study. In this case, the study sample is drawn from the overall population, both exposed and unexposed individuals with and without disease. This figure is another representation of a cross-sectional study and presents the relationship of the cross-sectional design to a case control study. The primary difference between the cross-sectional study and the case control study is with a case control approach, you're explicitly selecting the controls. In the cross-sectional approach, you're taking a sample of the entire population. Let's briefly review the analysis of cross-sectional data, keeping in mind that the objective of the analysis is to estimate the relationship or the association between the exposure and the health outcome. Because there is no temporality to the data, we can analyze cross-sectional data in a couple of ways. The first is the estimation of the point prevalence rate of disease among the exposed and compare that to the prevalence of disease among the unexposed. This approach is similar to the relative risk calculation in a cohort study, but the difference is there's no temporality to the data, and therefore the calculation is the point prevalence rate rather than the relative risk. In this simple case, the prevalence of disease among the exposed population is A over A plus B, while the prevalence of disease in the unexposed population is C over C plus D. The ratio of the two, A over A plus B over C plus D, is the estimate of the point prevalence rate of disease. An alternative approach to this would be to compare the prevalence of exposure in individuals with disease to the prevalence of exposure in individuals without disease. This is more similar to the case control analytic strategy. So using the same simple 2x2 table that you see on the slide, this calculation would be A over A plus C. That's the rate of exposure among the diseased individuals, and we're to compare that to B over B plus D, the rate of exposure among individuals without disease. So let's look at an example of a cross-sectional study. This is a paper published looking at the association between exposure to bisphenol A, or BPA, and measures of obesity, including BMI and waist circumference. The authors here are using data taken from the National Health and Nutrition Examination Survey, or the NHANES. NHANES is a cross-sectional study designed to assess the health of the U.S. population and to measure multiple environmental and other exposures in the population. NHANES data is collected cross-sectionally, but there's been multiple iterations over different years. But the sample each time is different, so it is not a longitudinal study. So here are the results of their analysis. You can see that they've estimated the odds ratio here, which is analogous to the case control design approach to the analysis. They've categorized the exposure to BPA by quartile and used the lowest exposure as the reference category. If you examine the data on the right-hand side of the table, you'll see that there is a significant association between increasing BPA concentrations in urine and the odds of being obese compared to being the recommended weight. So for example, if you look at the participants in the highest quartile of exposure under Model 1's assumptions, those participants are 85% more likely, the odds ratio is 1.85, to be obese compared to being the recommended weight. So what are the major limitations to this study? Well, because it's cross-sectional, you're not able to conclude that the BPA exposure occurred prior to the obesity onset. They've measured both of these, the obesity metric and the BPA exposure, at the same point in time. And here are the results of that cross-sectional study. What the authors have done is categorize BPA exposure by quartiles, so quartiles 1, 2, 3, and 4 corresponding to increasing concentrations of BPA in urine, and doing the analysis comparing overweight versus being the recommended weight and being obese versus the recommended weight, so the left and the right side of this table. And if you turn your attention to the right side of the table, the odds ratios that are being presented there are the odds of being obese compared to being the recommended weight by quartile of exposure. And you can see by the confidence intervals, not including 1, that there is a significant association between increasing concentrations of BPA exposure in urine and the odds of being obese. So what are the advantages and disadvantages of a cross-sectional study? Well, first, cross-sectional studies are generalizable because you're drawing from the population rather than an identified set of cases and controls. So NHANES is a really good example of this because the CDC takes great care to be sure they sample in a way that results in a study population that is truly representative of the U.S. population as a whole. Another key advantage to cross-sectional studies are that they're typically quick and relatively cheaper than other designs. The major drawback, as we've already discussed, to the cross-sectional design is the inability to distinguish the temporality or the time sequence between exposure and disease. So this might not be an issue in some circumstances, for example, if you're doing a genetic study or studying exposures that don't change much over time. But for many cases, that's not true, and the sampling of exposure and disease at the same time is a significant limitation. In addition to this, there's also the potential for bias due to the assessment of prevalence. This is referred to as the incidence prevalence bias. And this arises when the disease or the health outcome under study may be impacted by survival times.